In this video, we are set to explore why the middle term splitting method for factoring a quadratic equation, middle term splitting method, or you can people also call it factorization method to solve a quadratic. Factorization. Why does this method work is what we'd like to answer in this video. So to know why it works, we'll just look at the general procedure of solving a quadratic, what is taught to us. So if I have a quadratic such as this one, 3x squared plus 7x plus 4 equal to 0, I'd find two numbers whose product is 3 times 4, the coefficient of the first term and the constant term multiplied together. So this is my AC term if this were of the form ax squared plus bx plus c equal to 0. So my two numbers such that their product is 3 times 4 and their sum is 7. So what are those two numbers? If I am able to find these two numbers, they say that I can factor this equation. So maybe the two numbers are 3 and 4 themselves, because this thing is 12 after all. So this is 12 and 3 and 4 are factors of 12, and 3 and 4 also happens to satisfy the condition that they add up to 7. So maybe I can write this equation as 3x squared plus 3x plus 4x plus 4 is equal to 0. And now they say that I can factor this equation. How do I do this? Well, I factor out a 3x, and what I get is x plus 1 inside, and I factor out a 4 from the other two terms and I get an x plus 1, and lucky for us we have an x plus 1 again to factor out, and this happens every single time that we factor out. So in this video we'd explore why this happens, why this method of finding two numbers and changing these to the addition of those two numbers always happens that we get two factors in our final result. So after that, solving is very easy. So maybe if the product of two numbers is 0, means each number should have been equal to 0, or x plus 1 should have been equal to 0, or 3x plus 4 should have been equal to 0. And now I think you can continue, but what we are interested in is why the method is working. So for that, let us just consider a general equation, ax squared plus bx plus c. So let me just try to factor this. So I need it as the product of two factors, x plus something and x plus something else. I'd write this equation in that form. So for now, maybe I can say that a is equal to 1. So it's as good as not having a over here. So this is a simple case. We'll first tackle this one. So let me say that the factors are x plus some h I have, and x plus some k. H and k are just numbers here. So I am proposing that my factored form would look something like this. So which means if I multiply these factors out, x squared plus h plus k times x, you can verify this, plus h times k is my expression, the simplified expression for the same thing. So this is the same as this expression. So I'll take this equal to 0 off, because I'm just finding an analogous expression, a different expression for this very expression. So if I say that this is the same as that, then I could compare the coefficients of the two, coefficient of x square, coefficient of x, and the constant term. So what I see is the coefficient of x square is 1, so that's taken care of. The middle term's coefficient is b, but in the second equation it is h plus k. These both should have been equal for the two expressions, to be equal. And similarly, the constant term c should have been equal to hk. And isn't this what we are doing precisely there? We are finding two numbers h and k such that they sum up to the middle term and their product is the last term, if my a is 1, of course. So we have some intuition about what happens when we factor out an equation of the form x square plus bx plus c. So now let us get an intuition for what happens if we factor ax squared plus bx plus c, a general quadratic expression. Well, we can again argue that the factored form would look something like this: x plus some h times x plus some k, where h and k are just numbers, they can be any numbers. And now we see a problem that if we multiply these two factors out, I am proposing that this factored form is the same as this form. So the coefficient of all the x square terms, x terms, constant terms should have been equal, but the coefficient of x squared term in my factored expression is x squared, 1x squared. So the coefficient is 1. So I need an a somehow. I need an a. So maybe I could write an a up front in my factored form. Only then I would get the coefficient of x squared as a, and only then my assumption would be correct that this is the factor of that expression. Well, now we have a factored form, a new factored form. So like in the previous version of the problem, let us factor this. Let us multiply these factors, h plus k times, now we have an a out here and an x, and all of this calculation will pay off really soon. So this is ahk. Now I can compare the coefficients finally, because now I have the x square coefficient equal to a, which is alright for me. What about the x coefficient? I'll choose to a neutral color. A times h plus k should be equal to b, because the middle term's coefficient, and the last term's coefficient says that a times h times k should be equal to c. Okay, so this is interesting. So what I have found is a times h plus k is equal to b, so maybe I can multiply this out. Ah plus ak should be equal to b. So all this says is I'll have to find two numbers ah and ak such that their sum is b, and I'll have to find two numbers ah, and I need ak, something of the form ak, so maybe I can multiply out an a over here. If I multiply a on both the sides of the equation, this is what I am getting: ah times ak, as we needed, is equal to ac. So now do you see what's happening? We got two numbers that multiply to ac, we got two numbers that add up to b, and only if we find these two numbers we'll be able to write this equation into this factored form. So that's the whole reason why we do a times c, and then we find two numbers which multiply to a times c and which add up to b, and we do all this rigmarole, and we ultimately are able to factor out the factors magically every time. So this is the proof for that. I hope you found this useful. Thank you.